So, a previous video, I described what I'm calling my third approach to dealing with the Dirac Delta function, which is really just a modified approach of the way Paul Dirac did. He started with these two properties, and from these, you could derive this sifting property, pretending normal calculus works. That was kind of a pain. Or I could start with these two properties and derive this property. And going from here to there was a lot easier than going from here to there. And that's really the only reason to do it this way. Once you come up with these total of three properties, you're off to the races. So we can start with these two properties. Dirac delta function zero everywhere except at the impulse, and it has the sifting property. Those are the defining properties with this approach. The third property, that the integral is one, is easy to prove from the sifting property. And from there, we can start using normal calculus, pretending that it works with the Dirac delta function, and derive a bunch of stuff, which I guess is ultimately heuristic. It's the way Paul Dirac did things, I believe. But distribution theory kind of supports it. And I talked about that. Anyway, you can start deriving other properties using normal calculus. Most of them aren't too tough. If you want to see them all with the proofs, the heuristic proofs, see my website. But here's kind of the summary of them. A bunch of properties of the Dirac delta function. What its value is, the sifting property, the definite integral, the scaling property, symmetric, how derivatives work, product rule, it works just like normal calculus, even though the Dirac delta function is one of the two functions you're doing the product rule on, that it is the derivative of the unit step, etc. What its Fourier and Laplace transforms are. Those can all be derived from two properties, and then using normal calculus and heuristic proofs. But with those things, we didn't have to place a lot of restrictions on the function we're dealing with. Distribution theory would be the test function. It's at least got to be continuous and continuously differentiable in the neighborhood of the impulse. Beyond that, I don't think, with these proofs anyway, you're really putting a lot of restrictions on that function. Yeah, our choices are accept that this kind of works, even though delta t, this thing isn't a legitimate function, or use distribution theory and kind of ignore the restrictions on the so-called test function. Anyway, all this stuff is on my website. Here's the URL. Here's the URL or a web, how to find Dirac's original book. When he talks about the Dirac delta function, it's like one little subset of one chapter in a whole book on quantum mechanics. And a good little write-up on distribution theory is MIT professor's thing. Here's its PDF URL. I guess that's all I have to say. Except, okay, an epilogue to the epilogue, all this is, you can probably ignore all this. It just kind of bugged me, so I wanted to get to the bottom of it as far as I wanted to go down a rabbit hole. But you can see why most, especially engineering textbooks, don't bother with being super rigorous with this. It's like, here's a couple of principles or properties, take our word for it. And anyway, I'll stop there.